people. This is recorded not in class because the power went out and lost the recording from this morning. So here's a slightly shorter version of what we did in class. In class, we spent a little while at the beginning talking about the exam we just took. Nicely done. Most of you did really, really well. If there's some reason that it's been a problem, for instance, you were expecting to do really well and you're surprised at your grade now, email me, we can see what's going on. But yeah, overall, I was impressed. People did a really nice job. Other things, a reminder that today, I'll send an email about this out as well, but today you have your data sheets due. That's for lab. Yes, remember to get those done by tonight. I think that's it. I think we're on to today's lecture. So here we are. We're on to metabolism part 2. So the first portion of this was on Monday we talked about kind of the general idea of metabolism. Today we're going to talk about more about metabolism, about free energy and what it means. So for biological systems, we want to know which biological reactions happen spontaneously, happen without any input of energy, and then which ones are non-spontaneous, which one you have to pay for with energy. So to do that, we need to figure out what's happening in chemical reactions. So systems is called free energy. It's the energy that system can use to do work. It's called free energy, delta G. So don't worry about memorizing all this up here. It's just to salve my conscience so I don't just, tell you stuff without giving you the background. Basically, the free energy change is related to the total energy of a system along with the change in enthalpy, and the temperature. The take-home message is this delta G shows processes that whether or not it takes energy inputs to make it happen. So processes that have negative delta G's are spontaneous, and only these spontaneous processes can be used to perform work. So where you want to go with this? So many things. It's easier in class with people because they nod or shake their heads, but we can go. You can think of free energy. You can think of something like if you had a cliff and you have a ball on the top of that cliff there, right? So you have this ball and it's high in energy, and up there when it's high in energy, it's got a lot of free energy and it's unstable. It's not stable. As that ball goes over the edge, it falls. It drops in energy. It goes from being high energy to being low energy, more stable at the bottom. That change, that negative delta G, indicates a spontaneous process. So free energy, you can also think of it as how unstable the system is. So systems tend to move towards more stable state. So again, that ball up on the cliff, that's an unstable position for it. As things happen during a spontaneous change, this free energy is going to decrease, right? It's going to be moving towards the state of where it's the maximum stability. So if our ball would be lying there on the ground, bottom of the cliff, flat, right? Equilibrium's where you've reached the state of maximum stability. The process is spontaneous and can only do work if it's moving towards equilibrium. So we'll look at this picture here. The water on this side, right? This has a higher free energy than what the water over here does, right? This is unstable. It's going towards equilibrium. Over here, this picture, we see it's at equilibrium. It's at its most stable configuration that can be. So this process here has a negative delta G because it goes from high free energy to low free energy, goes down. Here, with that equilibrium, everything is solid. and just sorry, everything is stable. This change in free energy that's given off can be used to harness work. So as this water is going down towards equilibrium, it can power this turbine that powers this light. Once everything's at equilibrium, you can't harness anything here to perform work. So this picture right here is a closed system we're looking at. There's no water coming in, there's no water coming out. And so it reacts, it moves towards equilibrium, and it's done. But this isn't particularly exciting because, like, well, first of all, organisms don't exist in closed systems. And also, this is now done. There's nothing else here to really do. Like, everything's over. Even if you had a huge tank on this side, it still is going to move towards equilibrium and then stop. And good news is systems aren't closed. So just a second. This is going to be in 2 chunks. Sorry.